So now you learn, you have many models here. And however, we do not need to be, say, limited to one classifier for solving one problem. So why, there's no reason why we should limit to that. So you might ask here, well, suppose I have a, SVM, neural nets, and decision tree nearest neighbor. Can I combine them? Well, indeed, you can combine many learners, and together, in many cases, can give you better performance of that. So this type of methodology is something called ensemble method. So ensemble means you combine multiple predictor. In the end, you hopefully you can have better model of that. So once you combine them, and there's ways to, how do you combine them here? You can simply take a majority vote. So in the case of a classification problem, you have 10 models here, take a majority vote in terms of the predicted labels. So that's one way of doing that. You can also take a weighted combinations of different predictors. So there are various ways for doing that. So, so this here, what I'm going to do here is this. I'm going to talk about this several issues behind this ensemble models here. And in fact, in reality, people are simply take a very simple kind of unweighted average of different and take a majority vote of different models here. So this is very, very commonly used. And you train 10 different models. In the end, you take a unweighted average of 10 models here and the majority vote. And this seems to be work pretty well in practice. And many people use that. And in fact, it's highly recommend for your applications here. If you tried all the best for trying to identify the best models, in the end, you don't have anything else to try. And one remaining thing you can try is to generate ensemble models and take a majority vote among this ensemble models. So that's always one trick you can do. Of course, you can do a weighted average here, and then the combination, final decision here is going to be weighted combinations of different predictors here, weighted by this parameter alpha sub I here. And this weighted parameter here can be determined based on your training example. Say, well, if one predictor tends to do better than the other ones here, you weight it more here. So you can somewhat selecting those weights here based on the performance of each individual predictor based on the performance. So these are some of the heuristic way for doing that. All right. So one thing, what I'm going to do here, I'm going to talk about this specific techniques here. These are very commonly used in this community. Something called there are three different techniques here. There's one thing called a bagging. The second one is called a gradient boosting. The third algorithm called adder boosting here. And they represent different aspects of combining the learning models here. So I try to go over this very quickly with you because, it's actually very useful in practice. People very commonly wants to train the model and then combine them using these three different techniques. So what is the bagging? So bagging stands for something called a bootstrap aggregation here. So this bagging techniques originally came from statistics community. And in general, in the statistics community, there's a lot of questions related to estimation problems. And in the end, when people find the method to estimate those some variables of that, and the question, how do you know how confident is your estimation? And then one technique is using bagging, bootstrapping techniques here to estimate the confidence levels of your predictors. So how do I do that? Well, the way in the bagging here, what do you do here is, so you try to generate multiple models, but those models here are trained with slightly different sets of training data sets. And how do you do that? Well, what I can do is I can create a random subset of training data sets and through sampling. For instance, I can sample my training data set randomly, but with a replacement. So I have M samples here. I draw randomly M of them here, but with the replacements. What happens if you do this? It happens that some data are left out because it just, by chance, it didn't select by you, but some data sets are repeated multiple times. So you're going to have one data set here. Within this data set here, some training sample are represented multiple times, but then there are some original training data sets are not contained within this data sets here. So that will be representing one collections of training data sets. Of course, you can repeat this multiple times. We can repeat this k times of that. So what you can do this, for each one of these randomly sampled training data sets here, and you can use this random sample training data to train your models, build a classifier. And by doing that, so now if you repeat this k times, you will be able to generate k different classifiers. And once you have this k different classifier, you can combine them. And for instance, take a majority vote of this k different classifier in the end, and then you have a predictor for doing that. So this is a very classical methodology, something called bagging for doing this. Very straightforward, right? Very straightforward here. And so why this is helpful? Well, the reason it's helpful here is this. In general, once you average across different models here, you tend to reduce the variance of your models. And it just follow the law of this, you just follow the central limit theorem. If you have a k random variables here, if you average them, in general, reduce the variance of the models, variance of the average. And that happens here as well. If you have a k different predictor, each one of them has certain bias, certain variance of that. However, if you average them k times, in general, you reduce its variance of that. So that's the main benefit of bagging. It reduces the variance of the models. And once you reduce the variance, usually what happens is that it generalizes better on this unknown data sets. So the bagging is very commonly used on this model based on the decision trees. So think about this, right? We talked about the decision tree model. Suppose you use that for classification problems, and based on suppose you do not control the complexity of your models here. And in the end, you build a decision tree. It's very complex with the maximum depths here. And it can perfectly separate all the data in your training data set. So it looks like a decision, and the predictions of your input space look very complex, looks something like this. So that is one decision tree here. And we know that this type of models here is not good because it tends to overfit your training data sets. When you apply these models on new test data set, usually the performance is not good. So that's very well known. And how do we improve these models? What we can do is this. So the reason the model doesn't generalize well is essentially in the end, the model somewhat memorize everything in your training data sets. You think about it this way, because you use the entire training data as an example. So each of the data sets here is somewhat store your data in the memory, and then in the end you memorize them here. So that's not very helpful. However, if you use this bagging techniques here, and in that case, the decision trees here are learned based on essentially on a subset of data sets. And because when you do random sampling, some data are left out, was not used in the training here. And then hopefully by doing that, we discourage the model to memorize everything. And hopefully by doing that, hopefully it will generalize better. All right, so that's what you do here. What you can do bagging here. You train one model based on one randomly subsampled data set. You can do that with another randomly subsampled data set, and so on. You repeat this 5 times. So now what you can do now, you can combine these 5 models here and take a majority vote, and then you will have a classifier. So the main benefit of this type of approaches here is this. Once you take average of this 5 classifier here, you reduce the variance of your predictors. And however, the model is still somewhat a relatively low bias because you have full models here, so you can handle all the cases of that. So that can, in general, lead to a better performance of that by reduced variance while keeping the bias still relatively low. So you average. So this is the result. The average of 5 trees here. You can see now the model is somewhat smooth out a little bit here. This is the average of 25 trees. This is the average of the 100 trees here. The model tend to be more smooth version than the previous one. We use a lot of variance. So that is very simple to implement, and involves 2 stages. One is random sample the training data set, and then once you have data set, you repeatedly apply your models, train your model. If you use decision tree, that would be very straightforward for doing that. All right. So there's one particular types of a bagging model, something called based on decision tree, something called a random forest. So this is a model you can you can use based on some of the existing implementation, for instance, from scikit-learn in the Python, and then you can directly call the random forest model. So what random forest model is, consider two aspects. One is this, right? I use randomly sampled data to train my models and train many of them. In the end, I average them. So that's the one aspect of that. The second aspect is this. So there's a problem with the method I just mentioned here is this. Once you have lots of data, usually you tend to learn the same classifier. Because even if you are doing random sampling with replacement, but if you have lots of data sets here, what happens is that your data set tend to be pretty similar to each other, even after you're doing sampling. And so as a result, the average doesn't really help that much. So what random forests do is this. In addition to the random sampling here, at each step of training here, this method here only allow you to use only a random subset of features to build this decision trees. So that is another randomness introduced in this models here. Not only the training data sets here, but also what type of features that you can use to build the decision tree. Every decision tree is only based on a random subset of features. So by doing that, you somewhat encouraging models here to build up the more diversity of the trees, because each tree is based on different set of features. So of course, in order to achieve the same classification performance, so the different types of features ought to be used. So you somewhat encourage diversity, increase the spread of the feature across different sets of features of that. So by doing that, it somewhat reduces this. Because of that, random forest can do very well. It's very straightforward method. It doesn't need you to interfere with this method very much. Everything else is built in here. The only thing you need to do is probably determine how many trees you need to build here. And are you going to impose a maximum depth in terms of the complexity of each individual trees? And after that, the model can more or less do it all by itself. And however, in practice, many people found this model can do very well and very, very widely used. This is called a random forest model. So there's another type of models here. This is called a gradient boosting. That would be another very common, very popular ensemble models. So in the gradient boosting methodology here is this. So in the previously, the bagging here essentially is very simple. I randomly choose a subset of examples here. I build a model. In the end, I take average of them here. So the remaining two methods here treat different samples differently here in somewhat. So the idea is this. Well, another way of treating the ensemble model here is this. So in the boosting methodology here is this. Maybe you should focus on your learners, on examples that the previous predictor got wrong. Other predictors didn't do it correctly. If you can focus on to build a new predictor, try to focus on those type of hard examples, and then maybe you can achieve better performance. So this is very different from the random forest or other type of bagging methodology, because bagging method doesn't care about the sample. Every time it's random sample here. But for method, these two methods here, gradient boosting and adipose, they are based on something called a boosting methodology. So in the boosting methodology, essentially you focus on your model to try to make a prediction on hard examples. Those examples, the other model didn't do very well, and focus on that. And however, it depends on how you do this. You have two different methodologies for handling this. So one is called a gradient boosting. The second one is called the adipose. In gradient boosting, we're doing something like this. Right? Suppose you have this regression problem. This is the M-cycle data set we showed previously, and want to build a regression model, learn the relationship between Y and X here. Well, suppose I start with a simple predictor here, simply a thresholding function here, relatively simple here, right? So of course, this simple predictor is not doing very well, and doing very poorly on the left regions here, but relatively okay on the right regions down. Well, so that's okay. So, and then that's be first models here. And then for the next model, what I'm going to do here, I'm going to train a model, try to focus on those regions here, those examples here. The previous model did poorly, didn't do very well. I'm going to focus on that. How do you do this? Well, I'm going to focus on training models here instead of predict the overall Y here. but instead try to predict the residual between these actual labels and your previous predictions. And that's called residuals here. And now it's plot in this side here. You have the residuals here. So now Y here is not the target value, but it is this target value minus your previous prediction here. That you have this residual here, and you have X. And I'm going to focus on my models here, try to reduce this residual here. And then I train a new model for doing that. Well, I suppose you train a model, say I'm going to use another simple predictor here, try to predict the residual here. So now I'm going to focus on these regions here. So this region is the region, this samples here, previous model did poorly. And I focus on that and build another model of that. And once you have these guys here, you can combine these two into generate more sophisticated models here. Now become these two models here. By combining these two predictors, you can see now it's doing better. But you don't have to stop here. What you can do, you can continue the process. Now what you can do, you can calculate the residual between this new model, combined models, and with your target value. So now you have new residuals here. And you can say, let's focus on, make this hard example even better. And you can focus on these regions or these regions and so on. You can repeat this repeatedly. And the process for doing that is this main idea behind this gradient and boosting machine. So you can do that. Now your model becomes more and more complex here. And in general, your residual becomes smaller and smaller. And then because every time you try to build a predictor, try to reduce the residuals of that. All right. So this is called a boosting here. But however, why is called a gradient boosting? And the reason is this: in the gradient boosting machines here, it try to calculate this gradient of your loss function with respect to this increment you might be able to introduce into your prediction here. So what do I mean here is, suppose you want to predict the mean squared error between your predictions here and your target values of that. So now, once you already build one predictive model here, I want to improve that. Well, so you can directly improve the residual directly, but another way of doing this is this. I can calculate the gradient of this loss function with respect to this predictive function here to see which region I should increase, which sample I should increase. And then they can calculate this first order approximations of the residual. Instead of the residual directly, but a first order approximation of the residual. And then you're going to build a model, try to approximate the gradient or the first order approximation of the residual. And then you update them with a step size alpha. It's something like a gradient here, but the gradient is not with respect to any particular parameters here, but it is with respect to the residuals here. And that and you can apply this repeatedly, now give you something called a gradient boosting here. So it turns out this idea is here, relatively simple here. Essentially try to apply model repeatedly, try to improve the residuals, make the residuals smaller and smaller. So this gradient boosting machines becomes a very popular methodology. And in practice, many people, there's a lot of packages implemented that have GBM, stands for gradient boosting machine. One of the popular packages called XGB or XGB, I think. So there are these variants of the gradient boosting machines there. And those type of models turns out to be very powerful in practice. And as I mentioned that previously, so many of these calculus competition winners are built based on this gradient boosting machines of that. So it's kind of surprising. And maybe not surprising. So it's kind of a very general, very useful techniques for doing that. But they're built mostly based on decision trees. Essentially, every time you try to use decision trees and to build this, to model the residual, and then you add on top